So far, any question about we talk about the energy equation? I think previously we talked about energy equation in most of the cases, mechanical energy didn't contribution too much to the total energy. And this, we can also convert the Eckert number into the Maher number. Eckert number is same as the Maher number after you use the ideal equation to convert to each other. So basically, for the Maher number, you can see the speed of the sun and the velocity of your fluid particle. So basically, if your fluid particle compare with the speed of the sun is small, this value is almost like close to 0. So this number or Eckert number, they can be negative. That means this term and this term will be almost like 0. Okay, so let's for most of the case, your energy equation is reduced only to the thermal energy. I think this we mentioned in the energy equation, we just repeat one more time because during that time, maybe we didn't very detailed to discuss mechanical energy, their contribution. During that time, we maybe just said, for this energy equation, usually they can use this Fourier law to represent the energy equation before. But right now we discuss the contribution about the mechanical energy. these two, and the thermal energy about this one, how much they contribution to the total energy. So that's why in most of the cases, if your most contribution like 99% is just from the thermal energy. I think 1% you neglect 1% did not make your calculation have too much deviation, but your calculation time can maybe set like 90% of calculation time. So it's worse. Okay. So if we apply the non-dimensional parameter to certain of a problem, for example, we apply to the free convection problem. The first is a Gaussian equation, just like we mentioned. Then in the Gaussian equation, we need to see which one is the important parameter, which one is the important dimensionless parameter in the Gaussian equation. Another is we need to do the boundary condition, to do the non-dimensional boundary condition. Then we can solve the problem. So the first, for the free convection, we can apply our Gaussian equation. Which one is the important parameter? And this, I have give you the homework maybe last week or the week before last week. I forgot. It's the DIY homework 3 or 4. Okay, and for this free convection, basically important force is the buoyancy force. So this sounds like a new term in our Gaussian equation. So in our Gaussian equation, which one represents the buoyancy force? Remember just 1 hour before? The Gaussian equation, in the Gaussian equation, how many terms we have? The left-hand side is the inertial term, right? Then in the inertial term, this kind of acceleration will be changed by the gravitational force, by the pressure, and by the viscosity force. So about this free convection, then how we consider the buoyancy force? Buoyancy force corresponds to the pressure?
Yeah.
How?
Because the buoyancy force is fundamental definition just by pressure. Because we have a different pressure. Because we have a pressure different. So we can make the buoyancy force.
Anyone have a different idea? Gravity. Density. Yeah, but density corresponds to our momentum equation. So our momentum equation is like the inertial force equivalent gravitational plus pressure plus viscosity. Right? But first, someone said this is pressure correspond to the buoyancy force. Okay. You talk about density difference, but density difference correspond to your density difference. We let you in the gravity field lighter. For example, if you have a balloon, this balloon initially is like the air, but your balloon will not go up. But if in this balloon you use the fire, then this kind of air density change, but they can rising up. That's here gravity force. They become lighter in this gravity. So your change about this buoyancy force, basically you are changing your gravity. So your original gravity is like a T0, but the new temperature, like you increase the temperature, then your density change. This density change, then in the gravitational field, you will feel lighter than you go up. Similarly, if your temperature reduce, then you will going down. Okay, because the density become heavier. Then this is what I like to mention. Gradation number come from where? Come from the not mass continuity equation, right? Continuity equation didn't come out any dimensionless. Is this come out from the momentum equation or come out from the energy equation? Then they have a different kind of meaning. From the momentum equation, that means two different force ratio. From the energy equation, that means two different energy ratio. Okay, so you see it's come from the momentum equation. Energy equation. Okay. Basically, this is come from the momentum equation because we have a force. So one represent the buoyancy force. Okay, so today, earlier we didn't mention the ratio between this viscosity force compared to the buoyancy force. But sometimes, in most of the situation, you still have this kind of, for example, like in the heat transfer, Gradation number or the Ratios number, they are correspond to the buoyancy force with different kind. Sometimes the inertial force, sometimes like viscosity force in most of the case. But just like we mentioned in the momentum equation, this come out the flow number because the flow number is a gravity force compared with the inertial force. This potential non-dimensional, we said this is also similar to the Euler number because the Euler number is the inertial force correspond to the potential. And this is a common Reynolds number. Then how come they will come out of this? You just compare this and this. If you compare gravity force with the viscosity force, because the inertial force are the same, they will cancel out. Okay? Make sense? Okay. So your dimensionless is not only this divided by the right hand side, this become 2 to 1. You can use this divide every term. So this will become to the Reynolds number. this will become to a 1, this will become to a pressure compared with the viscosity force. This will be like a gravity compared viscosity force. In free convection, this term will become to this term. Okay? So, non-dimensional. It's not difficult, just there are lots of different arrangement. You can divide every term, then you will come out lots of dimensionless parameter. But some of them are repeat, some of them just invert. Okay? Okay? Okay, so basically this is from the momentum equation. Compare buoyancy force and viscosity force, and they just compare this term and this term contribution. If you want to see the total acceleration, then you need to see this problem flow number and the Reynolds number. Okay, and then you use the flow number and the Reynolds number, you can get Gratian number as well. Okay. Okay. Do I confuse you guys? Okay. Then usually non-dimensionalized boundary condition in the free convection or in the even in the forced convection, usually we use this fixed wall condition. The wall velocity becomes to 0, so this will become to 0 after. And this temperature will become to 1. So in particle, sometimes this temperature maybe is like 100 degrees C, 150 degrees C, but in non-dimensionalized, this will become to 1. Okay? So this is the boundary condition for so-called fixed temperature condition. Another heat transfer condition is like this. So anyone have an idea what's this condition? Fixed heat transfer. So heat transfer, they have two common conditions. Fixed temperature, fixed heat transfer. You only can choose one, okay? You have this, then heat transfer will become to unknown. You have this, temperature will become to unknown. So for this, you can see this heat transfer from the wall is same as the heat pre-convection that we take out. So basically, usually we will use a Newton number, different Newton number, to compare convection heat transfer, this term, convection heat transfer, and conduction heat transfer through the wall. Okay, so this is the usually common heat transfer condition use a Newton number. Compare two different kinds of heat transfer. One, convection. The other, conduction. And which one will be larger? I think most of you take a heat transfer, right? This time, convection and the conduction, which one will be higher? Let's represent the Newton number. If this is higher, Newton number always large than 1, right? So in your undergraduate, your Newton number is usually larger than 1 or less than 1. Using larger than 1. Using less than 1. Yeah, so everyone is clear. Usually convection is more effect compared to the conduction. You can see the conduction basically is less effect heat transfer because the particle didn't move. they only transfer to the neighborhood. It's just like everyone bring the bucket of water, they bring to your neighborhood by transfer. That's by heat conduction. But convection is you bring this bucket of water by yourself to some distance, then you pour out, then you come back to take another bucket of water. So depending on your moving, as long as you're moving, convection is the faster, this neutral number becomes too higher. So you can also compare the natural convection and the forced convection. Usually forced convection neutral number is much more higher than natural convection. Okay. And other boundary condition, I think this is more specific for the microfluid. I will not discuss this too much. If you are interested, you can take a textbook to talk about this. It's the Newton number, and yeah, there are some details to describe about this. summarize about this non-dimensional parameter, and also we give some non-dimensional parameter. Maybe we didn't introduce today earlier, but this we talk in most of our undergraduate class, like the wavelength number and the computational number. We will talk about this. As long as you have an idea about non-dimensional